to the 2026, what will we call it? Academic Decathlon focusing on math. This is worksheet number 1, and we're going to open up with the real number system. We're going to deal with radicals. So we have exponential notation, and then we have radical notation. So these are two different ones. Your base is y, your exponent is 2/7. This is your base, but now it's the 7th root of y squared. So that's the thing. So if we had to write this as an exponent, you would write it y to the 2/7. If we add these, you can't add like bases. That would just give you 2y to the 1/7 because we are adding them, so we combine their coefficients, not their exponents. This is going to be y to the 7/2. The exponent goes in the numerator, the root goes in the denominator. When we multiply, when we have a power of a power, we multiply. So that is going to be 2 times 1/7, which does absolutely equal y to the 2/7. And then, this is an interesting one. Okay, so let's write this as y to the 1/7 times y to the 1/7. And when we multiply like bases, we add their exponents. So you have 1/7 plus 1/7, which is y to the 2/7. So let's do it in green. So this one equals y to the 2/7. This does not, this does not, this does, and this does. So there are 3 expressions that are equivalent to y to the 2/7. That's kind of fun. That was a good one. I like that. Let's look at question number 2, simplify. So here we have some in radical notation and some of these problems in exponential notation. So let's decide which one we want to put it into. Let's put them all into exponential, I guess. So that's -7x to the 1/4, because 1 is their exponent, 4 is the root, so the root goes in the denominator, plus 12x to the 1/4 minus 3x to the 1/4. Now, since they are like terms have the same base to the same exponent, we're going to combine their coefficients. So we're going to take -7, positive 12, -3, leaving me with 2x to the 1/4. So -7, positive 12, -3 leaves me with positive 2x to the 1/4. Let's simplify. We have like bases again. When we have like bases multiplying, we are going to add their exponents. So that's 10 plus 3 plus 4 plus 2 over x squared, which will give me 7, 8, 9, x to the 19th over x to the 2nd. And when we divide like bases, we are going to subtract their exponents. So we get x to the 17th. That's nice and easy. We are multiplying like bases, so we will add their exponents. And you get m to the 39? M to the 39th. Yep, good. Everything else is pretty good. I like that. Let's go. Simplify. So this is interesting. So whenever it's multiplying, we can separate each of these into their own radical. So remember, there's a square. When we don't see a root, we know that it's a square root. And for every 2 inside, we know that x to the squared, the square and the square root cancel, and you get 1x out. So for every 2, 1 comes out. So we're going to get x squared rad x, and then we're going to get y to the second. So 2 of them come out. Notice the radical's gone here. And 2 of these come out with 1 left over that stays in. So we would not write it in this manner. We would write it with the things outside and then the things inside. So this would be my final answer. Because if we think about it, x to the 5th, the square root of x to the 5th can be written as square root of x squared, square root of x squared, and the square root of x. X squared, x makes 5 of them, all under the radicals. This will pop out an x. These will cancel popping out an x, and we'll be left with that x. That's how it became x squared x. And then this can be written as x squared x, because they're outside. So hopefully that helps you. Operate. Okay, these are like terms because they have the same radical. When they have the same radical, we're going to combine their coefficients. So we have 2 rad 3 plus 5 rad 3 produces 7 rad 3. Rad 3 can't be simplified because it's not a perfect square and it doesn't have a perfect square factor. You know, you could write this. This is an interesting one. We could write this as rad 27 to the 2/3, but that doesn't really help us. It kind of does, but doesn't. So instead of writing it in exponential form, I'm going to simplify this. So the 3rd root of 27 can be written, 27 can be written as 3 times 3 times 3. And so that can be written as 3 to the 3rd. So the 3rd root of 3 to the 3rd, notice this 3rd power and root 3 will cancel each other. So, and then if we just bring that square outside, because we're going to do that stuff first. So these cancel, leaving you with 3. Whoa, not to the 3rd. 3 squared. And you get 9. So this all simplifies to a nice clean number like 9. I know it's crazy. Before I start canceling division, I'm gonna do this exponent. Remember, orders of operations. Before we do multiplication or division, we have to do exponents. And mn squared, we can distribute exponents in, or we can just understand that that's mn times itself 2 times. It's squared, 2 of these. So we have m times m, which is m squared. N times n is n squared. Now we can subtract these like bases. So this is going to simplify to m to the 3 minus 2, n to the 7 minus 2. So division is subtraction. Gives us m n to the 5th would be our answer. All right, here's some interesting fill in the blanks using the word sometimes, always, or never. An irrational number to the 0 power never equals 0. Sometimes equals 0. Always equals 0. An irrational number to the power 0 always equals 1. So it never, we're going to write never equals 0. It always equals 1. The difference between 2 square roots of 2 non-perfect squares is rational, sometimes rational, always rational, never rational. The difference between 2 square roots of 2 non-perfect squares. The difference between 2 square roots of 2 non-perfect squares. So that could be the square root of 13 minus the square root of 15 is going to be, that's going to be irrational. That's irrational. But what if we did the square root of 8, which is irrational, minus the square root of 8? That's going to equal 0, which is rational. So that would be okay. So I'm going to say that it's sometimes Sometimes, oh, rational. Yeah, that's rational. So sometimes. Sometimes. This is irrational, this is rational. So it's not always, and it's never, and it's not never. So we gave a situation where it's sometimes. This is part B. That would be example B. Probably should have written it in. And then let's see. A rational number times an irrational number is always. Oh, look at that. Sorry, they tricked me. So a rational number times an irrational number is sometimes. Sometimes irrational. Sometimes. So my knee-jerk reaction was that it's irrational because 3 times the square root of 2 is going to equal an irrational number, right? That's a rational number times an irrational number produces 3 rad 2, which is irrational. However, if you take 0, which is a rational number, times an irrational number, well, that's going to equal 0, which is rational. So it is sometimes. All right. That's a nice, gentle, easy first worksheet. Hopefully you enjoyed it. And here are the answer keys. I don't know why they started with 4. That was kind of weird. But I am not the academic decathlon coordinator. Come to me if you have questions.